Hello! 8.6! We are going to be solving linear systems.
How?
Using matrices!
Wicked.
Alright, we've solved via elimination. We've multiplied some equations to get equivalent forms. We've added them together. Life is good. Doing that, we've changed coefficients, but variables remain in place. Using matrices allows us to just focus on those coefficients without those pesky variables getting in our way.
So annoying.
The worst. When we're solving using matrices, we need to make sure that all of our constants, our numbers without variables, are on the right side of the equation, on the equal sign there, and the variables are organized onto the left. So organized in order, so X, then Y, and then if we have 3D systems, then Z. Okay? To create a matrix, this is what it's going to look like. We're going to have square brackets around the entire thing. We're going to replace the column of equal signs, so instead of having equals lined up on top of each other, we're going to just have this long dividing line, and then we're going to erase all of the variables. So the way that is going to look is that we have this big square bracket here. We are going to put 2x plus 3y is equal to 7. I'm going to write them all out and then erase all the things that we don't need here. So this is what we would normally do, but now we have the square brackets. When we're talking about matrices, we are getting rid of those equal signs and just replacing it with this long dividing line. So it divides my left-hand side with my right-hand side. We are also not including any of our variables. So by x, by y. And if there's a plus in there, we don't have to include the plus because that is automatically assumed. So this is how we would make our matrix for this system of equations. We could do same with this next system. So here we would have 4 because that's the coefficient for x. We'd have 1 because that's the coefficient for y. Or a giant dividing sign. And on the right-hand side, 0. For our second equation, we have 3, that's the coefficient of x. 2, that's the coefficient for y. And then 10. And then we've done.
The operation's the same when you look at 3D systems. Nothing really changes here. It's just like we're throwing some square brackets around there, turning that equal sign into a giant bar, and then getting rid of all those variables. So in this case, we'll have 3, 1, 2, 7 for the first row, representing the first equation. We'll have 4, 2, negative 1, 12, representing the second equation. And the third equation is 3x, negative 2y, positive 8z, resulting in a value of negative 5. And we do this one more time. Matrix, coefficient of x is 1, and we have 3, we have negative 1, that equals 7. And we got 5, negative 4, negative 1, negative 2, and 2, 1, negative 2, negative 1. So that's how we can make a matrix based on a system of equations.
But at the same time, we could work backwards. If we're given that matrix for our system, we could also go ahead and say, well, what are those equations? Here we know that there's going to be 3 equations, right? Equation 1, equation 2, equation 3. We know that because we have 3 rows here. So we'll have equation 1, 2, and 3. My system that I can choose to be modeled by this matrix can use the variables x, y, and z. I know instead of this dividing line, that's where my equals goes. So if I wanted to write a system modeled by this matrix, I could say 2x plus y plus 4z is equal to 16 for my first equation. I can write x plus 3y minus z is equal to 4 for my next equation. And I can write x minus 2y minus 2z is equal to negative 11 for my third equation. Cool beans?
Yeah, the beans are cool.
Yeah.
When we're solving these equations using systems using matrices, what we want is to have a diagonal of 1s and have everything else to be 0. Reason being, when you look at this thing, if we interpret it, that tells us that x equals 3, and the second row tells us that y equals -4. There's no other variable in each one of those lines. It gives us something very directly. That's why that's our goal. Well, what we can do here, once we have this in its matrix form, is really start adding lines together or multiplying lines by something. Any of the same kind of transformations you did when solving by elimination. In elimination, you might have said, we're going to take equation 1 and we're going to take equation 2 and we're just going to add them together. And that got you this. Thing is, we just need to make sure we store that somewhere. So this new equation, where does it go? I would like this to be a 0. So I'm going to say that in my next line, I'm going to take row 1. I'm going to take row 1. I'm going to add it to row 2. Just like we took equation 1, added it to equation 2. I'm going to store that somewhere. I'm going to store that up in row 1. So I'm replacing my current row 1 with what happens when I add those two rows together. So my bottom row, nothing changes. Still as that. My top row, row 1 plus row 2. So I'm checking out 2 plus 3, which gives me 5. 1 plus -1, which gives me 0. 7 plus 3, that gives me 10. And that's exactly the same thing that is represented by this equation that we would have gotten if we pursued this using an elimination method. We're just not writing coefficients so much anymore. As the famous Miss T would say, any hoozles, we're going to move on. We've got a 0 there. That's nice. We want this eventually to be a 1. We want this eventually to be a 0. We want this eventually to be a 1. Whatever you see that you can do, go with it. Personally, once I have a 0 there, I'm gonna make this a 1. I'm just gonna divide the entirety of row 1 by 5. Again, I haven't changed row 2. That's still this. But row 1 is getting divided by 5. 5 divided by 5 is 1. 0 divided by 5 is 0. 10 divided by 5 is 2. And at this point, this row really tells us that x is 2. We just don't know what y is. That's aight. We're going to finish this thing off. Get out of here, random info. I, at this point, would turn this into a 0. But how would I do that? I need to add some combo of row 1 and row 2 together to get there. Well, if I take this and I get rid of 3 of those, that should eliminate it entirely. So I'm going to take row 2. I'm going to subtract 3 of row 1. And that will be my new row 2. So row 1 is the one I'm not changing this time. Row 2 minus 3, row 1. So this minus 3 of that is 0. This minus 3 of that is -1. This minus 3 of that, oopsie daisy, is -3. And for a last step, we've got a 1, 0, 0 there. This just isn't a positive 1 yet, so all I need to do is, how you say, multiply it by -1. So row 2 will become its own opposite. Row 1, same. Row 2, yikes. I spotted this myself. No one pointed it out for me. I am a liar. Row 2 is its opposite. Opposite -1 is 1. Opposite of -3 is +3. And at this point, you could state this a variety of ways. We're used to saying just x, y is equal to 2, 3. Or if you want to get real fancy-dancy, you could say this. Je ne care pas. You can choose whichever one you want. Just follow your heart.
All right. Oops. Let's try another example. But again, same process. So when Mr. A was doing this last example, there's a couple of things that maybe you want to do in a different order. That's all right. Realistically, when you're solving using matrices, it doesn't matter which order you accomplish a lot of your tasks in, as long as you are trying to aim for that same end result. Okay? So at the end of the day, if your answer is still the same as what we get, then you're all good. So here we're going to start by creating a matrix. So we have 2, 3, and 10 in our first row. And our second row here becomes 3, -2, and -11. Okay. What I am going to do is I am going to kick things off by just, I don't know, I'm going to aim for getting a 1 there, right? Because what I noticed is if I take my 3 and I add it to -2, I notice that I get a 1. So I'm going to replace row 2 with row 2, but I'm going to add row 1 to it, just so that I can get a 1 in this spot over here. All right, so row 1 stays the same. So I still have 2, 3, and 10 along the top. And row 2, well, 3 plus 2 becomes 5. -2 plus 3 becomes 1. And -11 plus 10 becomes -1. Alrighty. Next thing I want to do. My game plan here is I like to get rid of this. I have a 1 at the bottom there. I want to get rid of that 3 at the top. I want to make it a 0. How could I do that? Well, if I take this 3 and then subtract 3 of my row 2s from it, well then adios muchachos, you are going to disappear. So my row 2 is going to stay the same. My row 1 is the one that's going to be doing the changing. And here I'm going to take row 1 and I'm going to subtract 3 of my row 2s. Okay. So row 2 stays all the same. Life is G for row 2. But row 1 is going to be disappearing here. So I have 2 minus 3 times 5, so 2 minus 15, which gives me -13. I have 3 minus 3 times 1, so 3 minus 3, which gives me 0. And here I have 10 minus 3 times -1, so I get 10 plus 3, which means I get 13. Oh, this is kind of nice, because what you might notice is in row 1 here, I want to get a 1 in this spot here. I want to get a 1 in that top left corner. To do that, I'm going to have to divide that by -13. And the reason that I said ooh as well, we'd have to do it anyways, but this here is a 13, so dividing 13 by -13, ooh, that's nice.
It's a top tier division.
Yeah, it's one of the gooders. So, in this case, I'm going to take row 1, or my new row 1, and that is going to be row 1 divided by -13. So, -13 divided by -13, that gives me +1. I actually really hate that bracket, how that turned out. I'm so sorry.
It's okay.
Thank you. Alright, so I get 1. 0 divided by -13, 0. 13 divided by negative 13, negative 1. My row 2 stays all the same. Oh, so nice. Now, I've got a lot of good things working for me here. I have a 1 here on this top of the diagonal. I have a 1 here at the bottom of this diagonal. I've got a 0. All I need left is to get this 5 to be a 0. And how do I get that 5 to be a 0? Well, if I take this 5 and subtract 5 of my row 1, that should be able to do the trick. So, my row 2 is the one that's going to be doing some changing. And I'm going to take my row 2 and I'm going to subtract 5 of my row 1. So, row 1 stays the same. And row 2 goes 5 minus 5 times 1, which is 0. I have 1 minus 5 times 0, which is still 1. And negative 1 minus 5 times negative 1. Whew. So that's negative 1 plus 5, which gives me positive 4. Now I have all of the desired things. I have 1. Ooh, where'd you go? Come back. Oh, whew. Thought I lost you. Here I have 1s along my diagonal. I have 0s everywhere else. And I am ready to state some final answers up in here. So,
up in here.
I could state it in the same way that we are used to from before. X, comma, y, and that would be negative 1, comma, 4. Or I could state it in this new matrix way that was introduced to you by Mr. Thide last example.
Heckin' right.
Where I said x, y in its own matrix is equal to 2, 3. Oh, so nice.
So nice.
Alrighty. So that is your basic solving by matrices. But the nice thing about matrices is that we can also use it to solve 3D systems!
Woo! Yeah, for two-dimensional systems, the amount of brain power I expend on this is way more than I would ever want to put in for a 2D system. I would personally just go with elimination or substitution every single time. And I favor elimination, but I wouldn't use matrices for 2D systems. They are great for 3D systems, and if you have a 4-dimensional, 5-dimensional, 10-dimensional system, woo, the things you can do are wicked cool. How many examples do we even have? Oh, just the one, hey? Boy, how do you want to exchange banter on this? Do I do the whole thing?
You do a step, I do a step?
Yeah, okay. Okay. Alright. First step is probably to get this into a matrix. Last step is going to be to get it to look like that. Where again, we have 1s following this diagonal, and then 0s everywhere else. Because if we were to interpret this one says that x is straight up 4. This one only tells us that y is negative 1. This one tells us that z is 9. There's only one variable that has any meaning in each row. Makes life a little bit easier. I don't know what colors you used. I like this. I love that blue. Anyways, it's matrix time. So I'll set up my matrix. Have we solved this system before? Is this from a previous example?
I don't remember. Let's see.
The numbers just look... I swear I've seen the number 1 before.
This one. Oh, yes.
Yeah, we did?
We did. Check out 8.5a.
Whew. It's like the first
if you
example.
want to double check your final answer.
Neat. So we should be getting a nice answer out of this. Alright. Let's figure out what we want to do. I don't even know. I'd probably do something involving these 1s, to be honest. In fact, I like that 1 right there. I think I'm just going to use that to make these into 0s. So I'm going to brace yourselves. I'm going to replace row 1 with whatever I get when I take row 1 and add 3 row 3s. Because if I take this and add 3 of those, I get a 0. And I kind of want a 0 right there. I'm also going to take row 2 and I'm going to replace it with row 2 minus 2 row 3s. Because if I take this value and subtract 2 of those, then I get a 0, which is exactly what I want right there. Woo! Barba! I'm just going to shift this whole operation down a bit. Gotta keep this neat and tidy. So row 3, no changes. Let's do this. Row 1 is row 1 plus 3 of row 3. So I need row 1 plus 3 of row 3. 2 plus 3 fours is like that many. This plus 3 of those. And I need this plus 3 of those. Whew, I got that 0 that I wanted. Oh, and this plus 3 of those. And then row 2, let's tackle this. Row 2 is row 2 minus 2 of row 3. So I'm going to take this and subtract 2 of that. Element by element, this minus 2 of that. This minus 2 of that. This minus 2 of that. And this minus 2 of that. Neat.
Awesome. Alrighty, so the next thing that kind of jumps out at me here is if I'm looking at that row 2, ooh, she's getting real close to just having a 1, then a whole bunch of zeros.
That's pretty nice.
And so what I'm going to do is, in this time round, I am going to take my row 2, and I'm going to replace it with my row 2 divided by -1/5, because I want that to become a positive 1, and I want it to divide by 5 at the same time. Oh, I'm dividing, sorry, I'm multiplying by -1/5, or dividing by -5. Alright. To do this here, whoop-de-whoop, my row 1 and my row 3 all stay the same. So I'm just going to let them be.
Let them be.
And my row 2, well, -5 divided by -5 becomes 1. 0 divided by -5, 0, 0, 0. Oh, so nice.
It's pretty nice.
And because that took, like, no time at all, I am just going to continue with the next step as well. Alright, what I see next is I want to just get rid of these guys and make them into zeros. I really want to do that. I want to do it so badly. You don't even understand how badly I want to do that.
No, I understand it.
Ah, good. So, to do so, I am going to take my row 1, and what that is going to become is that's going to be row 1 minus 14 row 2s. Whew! And my row 3 is going to become row 3, but minus 4 row 2s. Whew! So, let's tackle this guy here first.
Okay.
Get my matrix color out. Again, my row 2 is going to stay all the same, so I'm just going to write that in. Now, row 1 is subtracting 14 row 2s. So I have 14 minus 14 times 1. 14 minus 14 is 0. Now I have 2 minus 14 times 0, which is 2 minus 0, which is 2. I have 0 minus 14 times 0, which is 0. And I have 8 minus 14 times 0, which is still 8. In row 3, this is what we're tackling now. We're doing row 3 is equal to row 3 minus 4 of my row 2's. So in my first term, I have 4 minus 4 times 1, which gives me 0. I have 1 minus 4 times 0, which keeps me with 1. I have 1 minus 4 times 0, which keeps me at 1. And I have 3 minus 4 times 0, which keeps me at 3.
We're getting hecka close. The more we see these zeros popping in, the better life just generally is. Looking at this row, we've got 2 slots filled with zeros. It's just this one that needs to be a 1. Okily dokilies. Let's just continue on down. Whoop, we're out of room. So let's go elsewhere. Boop. Ooh, I could do better. Just give me a sec here, everyone. Oh, it's fine. Any case, here's what I'm going to do. I'm just going to take row, what are they doing? Row 1. And divide everything by 2. So row 2 is staying same. I could do more space there. Row 3 is staying same. And row 1 is getting divided by 2. 0 divided by 2 is that. 2 divided by 2 is that. 0 divided by 2. And 8 divided by 2. Oh, we're so close. What are we doing with my life? Selecting this pink. So we can go to my next step. And in my nextest step, there's 2 1s in this column. Not ideal. I need that one to be a 0. In that case, I'm going to take row 3 in purple and subtract row 1. And that's going to be the new row 3. Row 3? Yeah, row 3. So I'm keeping row 1 same. I'm keeping row 2 same. I'm changing row 3. I'm taking row 3 minus row 1. So this minus this is 0. This minus this is 0. This minus this is not 0. That's 1. And this minus this is negative 1. This does give us the right answer. We could leave things like this realistically. Personally, I like to have everything laid out so that we have the ones in that diagonal and then the zeros everywhere else. Question is, what did I just do to get there? I swapped these 2 rows. So that's what I'm going to do. I'm going to take row 1. I'm just going to swap it with row 2. Row 3 stayed same. And rows 1 and 2 swapped around there. And we can now state the solution. A 0, a 4, a negative 1. Or if you want to be all fancy-dancy. That's that. There is some practice work. And solve some systems. Ooh, some nice 2D systems. Some 3D systems. But even a 4D system and a 5D system. It's pretty wicked. Give it all a try. Give it a go. Give it a shot. And just let us know how it went. Like, hey, Mr. A, hey, Miss T, I'm really getting this. Or, hey, Mr. A, hey, Miss T, this is terror. I can't remember if I said this earlier, but we will never ask you or say that you have to solve a system using matrices. It's just an option that's out there in case you enjoy it or find it very usable.
The cool thing about matrices is that it's kind of like a puzzle, at least in my mind.
Yeah.
It's like a fun little math game. But also, if you understand this, there's actually quite a few courses in university
What?
that you can take that are all about linear algebra, and I'll talk about matrices and things like that.
There's a course in university that talks about linear algebra? What's it called?
It's called linear algebra.
Wow, what a name!
Yeah! But they talk about all the things matrices like. So things like this that you're doing, you can see be built upon in that course. So if you're really just loving this,
I love it.
oh my gosh, same. And if that's something that you want to pursue because A, you think it's fun, and B, you could get a university credit for, whew, so nice.
Yeah. Well, Tibbs, is there anything else you want to say?